Hi, everybody. Dr. White here with some recap on Chapter 4 homework, few selected problems for special comment. First of all, section 4.1, number 6. This was the one about the four different quality levels of bolts, and there's like 25 bolts, and each bolt has a certain chance to have one of four quality levels. And you were supposed to find the chance of that in your 25 bolts, that 7 would be very high quality, 8 would be high quality, 6 would be average, and 4 would be low quality. So you could go to this section and study the multinomial distribution and pull out the formula for the PMF for a multinomial distribution. That's totally okay. But note also that this is the sort of probability problem that you already know how to solve using basic principles. So I'm going to use that approach here. First of all, I just want to find what's the probability that in your 25 draws, your 7 V's come first, followed by 8 H's in a row, followed by 6 A's in a row, followed by 4 L's in a row. So you know by the independence of your draws that it's going to be this product. Okay, but that's only, this particular sequence is only one out of many, many ways that you could get that particular tally of the different kinds, okay? So what you really have to do is you've got to multiply that probability by the number of ways to rearrange 7 V's and 8 H's and 6 A's and 4 L's. That's the problem of how many ways are there to spell a word with those letters. And we have figured out how to do that in the past. There's 25 total letters here. And so the number of ways is the 25 factorial over the correction that you do for rearranging each of the letters. So multiply that by this and you're done. Okay. 4.1, number 8. Let's look at part C, because that was the most complex of the sample spaces, I think. So I've got a picture of it here. And what I noticed was that there are 4 lines you can draw that bound the points of the sample space. And when you stare at their equations for a little bit, you get that one of them is y is x plus 2, another is y is x minus 2, another one is y is negative x plus 6, and another one bounding the bottom down there is y is negative x plus 2. So the sample space can be written as a set, as the set of all x, y, and the integers cross the integers, such that y is less than each of the top bounds and bigger than or equal to each of the bottom bounds. So those 4 things all have to hold together. Once you've done that, you don't actually have to make any explicit restrictions on the x's. They are already, the x values are already determined by these relationships between the y and the x values. Okay, so that was the challenging part of this problem. The other part, getting the marginal for x and the marginal for y, was not problematic for anybody. But notice they're the same marginals, and that makes total sense because when you look at the sample space, it has 90-degree rotational symmetry. If I rotate it 90 degrees, I have the exact same set. And since each of those points has the same 1/13 weight, then which axis you call x and which you call y doesn't make a difference. And so the 2 marginals have to be the same. Always want to look for kind of patterns and insights, geometrical insights like that, so that your work is not just kind of numerical computation, but also integrates geometry, pictures, graphs, and other types of insights. Along those lines, I want to look at what was probably the most lengthy of the problems, number 4.4, part 6. So this is the one where you have this PDF for a bivariate continuous type random variables. The support of both the x's and the y's is between -1 and 1. And you're supposed to find such things as the variance of x and the variance of y. So tell you what, I am first going to just find the marginal distribution for x, and then I'll go and get its variance. So that's one way to approach the problem. So if I want the marginal distribution of x, I'm looking for f sub capital X of little x at any little x. So by definition, it's this. And the support on the y here, the y's variable integration, support on the y is from -1 to 1, so I can cut the integral down like that. And within that support, that's my formula for my f. So the 3 halves x squared is a constant as far as the y is concerned. You can factor out, and I just got to do this little integral right here. Now you can get that integral in a couple of different ways. You could be kind of graphical about it. You could say, let me graph 1 minus the absolute value of y. So you might start by graphing the absolute value of y, which is that, that little bent upward going triangular type shape. And then the graph of negative, the absolute value of y, would be the same thing flipped over the y-axis. I'm using a z-axis as my vertical axis here because I'm using y as my variable. And then to get this thing off of this thing, we would just add 1 to it. And so when you add 1, you raise the level of every point on the graph by 1 unit. And so you're left with this, and I only care about the y's from -1 to 1. So you're looking for the integral of that. So you're looking for the area underneath that triangle from -1 to 1. Great, so you want the area of a triangle, 1/2 its base times height. Now the base is 2 units from -1 to 1, and the height goes up to 1 on the y-axis, so the area is a 1. You could also just be more analytic, and so you could say, well, let me get this integral by considering that I have to find a way to take off these absolute value signs, before I can get antiderivatives and use fundamental theorem of calculus on this integral. And so I notice that for the y's from -1 up to 0, those y's are negative, and so their absolute values would be their opposites. And for y's that are from the 0 to 1 within that range, that should say just y is bigger than 0, not absolute value of y bigger than 0. So I'll make that change, although I don't think you'll ever see a PDF of this. Yeah. So anyway, since the y is positive, the absolute value of y would just be y. And so you take your whole integral and you break up around the change point of 0 into these two integrals, this one here and this one here. And in each one of them, you can drop the absolute value signs. For this integral, you replace it with the opposite of y. And for this integral, you replace the absolute value of y with just y. And so you get these two integrals to work on, and they're both pretty easy to work on. And after you simplify a bit, you get your 1 again. Okay, so that's kind of a more boring way, but it's also totally correct. Now, it's kind of interesting that this turned out to be 1, okay? Because that, the -1 to the 1 is the support of the y marginal. And so saying this integral is -1, is it saying, that piece of the PDF for the joint integrates out to 1. I bet that actually the PDF for capital Y will be 1 minus the absolute value of y. And we'll confirm this with the more standard definitions in the usual math, but that actually is correct. So anyway, we now know this. We know that it's the 3/2 x squared that was sitting on the outside of the integral up here. And that integral is 1, so we just get 3/2 x squared. And so that's also kind of interesting because this part, it only involves x's. as it should, but that was also like this other factor in the f of xy joint density. Okay, so the book basically skipped all that work of finding the marginal for x. And then it went in and said, okay, we're going to compute expected value of x when they were working with the example, that this exercise is based on. They just skipped all that stuff and they went right, to here. I'll start here at the absolute definition of expected value, but the support of f sub capital X is -1 to 1. And so we get what we had in the book, and we compute like what the book does, and we end up with 0. Now, I'm interested in the variance of capital X. So my strategy is to use the shortcut formula for variance. So I'm going to need the expected value of x squared. So that would be the integral over all the possible values of value, x squared, times chance of getting that value. And so I have this integral to do, which is not hard, and it works into 0.6, 3/5. And so then the variance will be that 3/5 minus the square of the expected value, so it's just 3/5. Ta-da. How about the variance of y? Well, let's go ahead and actually use the strict definition to confirm that the marginal of y is what we suspect that it is. So we pull out the definition. So here we are integrating with respect to x. The support on the x is -1 to 1. So we're integrating that same stuff, but with respect to x now. So it's the 1 minus absolute value y that can come out. And then we have that pretty easy integral to do. And sure enough, there's a typo here. That should be a minus a half, not a plus. And we work it out. So it's a 1/2 plus a 1/2, which is a 1. And then we just left with this, just like we expected. And so now we can go and we can get the expected value of y, which the book, kind of did, skipping the step of finding the marginal, turned out to be 0. And the expected value of y squared, we need to get ourselves so that we can apply the shortcut formula. And so let's take a look at that. Integral from -1 to 1, y squared times chance of getting that value. So actually, if you think about this integrand here, just think of it as a function here of y. So here we have z is y squared times 1 minus the absolute value of y. That's a y squared. That's an even function. If you plug in a minus y where you see a y, you still get the same z value. So it's an even function. It's symmetric around the z-axis. And so that means that the integral from like -1 to 0 would be the same as the integral from 0 to 1. The areas underneath on both sides have to be the same. So I'm just going to do twice the integral from 0 to 1. And between 0 and 1, the absolute value of y is just y. So I do a 1 minus y here. Dropped off my dy that should still be there. There we go. There should be dy right there. But my dy made it back in. Here I've just multiplied through, applying the fundamental theorem of calculus. And look at that, like I don't have my vertical line. Well, I do. It looked like it just didn't like come out. I'm not sure what's going on there. There should be like a vertical line and a 0 to 1. So that is so weird. Yeah, okay. But anyway, you plug in 1 and you plug in your 0, and you only get stuff when there's the y is a 1. And so I work a little while and I get a 6th. And so applying the shortcut formula, I've got a 6 for the variance. Okay, so that part of the problem was, not that bad. Let's do part B now. So that was finding the probability that -x is less than or equal to y. And so looking at my entire support, I draw the boundary line negative x equals y, or if you like, y is negative x. And the y has to be bigger than equal to negative x, so you're in this like upper triangle here, and you need to integrate the density over that upper triangle, okay? And when we set this up in class, we tried vertical strips, we tried horizontal strips. We didn't complete either method, but we figured it was going to be a little bit simpler if we used the horizontal strips. So that's what I'm going to do here. I'm picking an arbitrary y level, anywhere from as low as -1, where that would just be a 1-point strip, all the way up to y is equal to 1, which would be the longest possible strip. Okay, and so what we need to do is add up from -1 to 1 the area underneath the F curve along that strip. So we need to identify the leftmost value of x in terms of y and the rightmost value of x in terms of y for that strip. And within that strip, f of xy will have that formula. Okay? So we have an inner integral with respect to x. Its limits are going to involve y. And then we have this outer integral involving the y. Its limits are just the numbers. So when we look at it, the leftmost x is where x is minus y. And the rightmost x is, vertical line here, where x is 1. And so now we've got our left and right x. So now we just have to deal with the fact that there's an absolute value sign here, which we need to remove. And so we think again about how y is going from -1 to 1, changing its sign around 0. So I really need to break this one integral up into an integral from -1 to 0 plus an integral of the same stuff from 0 to 1. And from -1 to 0, where the y is negative, the absolute value of y is opposite of y, and the absolute value of y is just y over in this other integral. So simplifying a little bit, this is a 1 plus y, which we can drag outside of the inner integral. And here we have a 1 minus y that we can drag outside the inner integral. And I'm noticing that both of the inner integrals here and here are the same expression. So let me just go ahead and get that expression in terms of y. So I just evaluate this integral best I can, and I get 1/2 plus y cubed over 2. And so I'm just going to stick that in, here and here, okay? And so I end up with like this, okay? And at this point, I guess I could take the halves outside of the integrals, and I could multiply. I could like FOIL out this, and I could FOIL out this. And when I do, I get this for the first integral, and I get a couple of negative terms here in the FOIL on the second integral. And then I just apply my fundamental theorem of calculus. So that's this step here. And then I evaluate between the specified numbers. Putting in 0 doesn't give me anything. Subtract off what you get by putting in the -1. Over here, you'll only get something by putting in the 1. And so you stare at your stuff for a while and simplify, and a couple of things cancel, like this -4th is going to cancel this +4th, and the 1/5 is going to cancel -1/5. And the other stuff, there's 2 1s, and they combine to a 2, and there's 2 halves that combine to a -1. 2 minus 1 is a 1. So I'm looking at that half on the outside times a 1. And so the answer is 1/2. And as soon as I see that, I get really suspicious. Gee, did I really have to go through this kind of longish calculation? And of course, you always want to do that when you're working with math problems, but especially with the ones from this book, because they seldom make you do a long calculation. They seldom force you to do a long and meaningless calculation. They may give you the option to do that, but they may also be kind of like inviting you to see if there's some insight into the problem you could make that simplifies matters greatly. In fact, when I saw this, I kind of thought maybe there's some symmetry in that function f of x, y, in our uh, in our bivariate PDF. So let's investigate that a little bit more. So f of x, y is this stuff, on this square. And what I'm going to do is just plug in an opposite of x and an opposite of y wherever I see an x and a y in the formula. And I get this, and that just reduces to f of x, y. Okay, so f of opposite of x, opposite of y is the same as f of x, y. Think about that geometrically. Here's that support. Here's that square. This is the origin here. Here's the x-axis. Here is the y-axis, okay? And here's our little boundary line, coming down here. That's our y equals minus x line. And, we're interested in the volume underneath f over that top triangle. But I want you to notice something. Like, say you let x, y be a half 3/4, which is right here, denoted with this dot. The opposite of x, opposite of y, would be minus a half minus 3/4, which is down here. Okay, it's like right across the origin from xy. If I just went straight through the origin, I would hit that opposite point, and the distances are the same, going in, coming out from the origin. Try another example. What if xy is negative 3/4, 7/8, which I marked with the point up here? The opposite point is down here. And again, if I took a straight line and started here at this x and just drew through the origin after traveling the same distance to the origin and then from the origin, I would arrive at the opposite point. So what's happening is that f of xy is symmetric around the origin. If I were just to, the graph of f is some surface over that triangle. But if I were to take that surface and just revolve it 180 degrees around the origin, it would revolve exactly onto the f surface that's over the bottom triangle. Therefore, the volumes underneath them are the same. But the volumes underneath them add up to the volume underneath the entire sample space, which has to be 1. Therefore, this volume and this volume both have to be a half. So therefore, the probability that we seek, which is that quantity right there, is a half. And so this problem can be solved by symmetry. And I should point out, when you've got a PDF that's symmetric around the origin, like this one is here, okay, then any boundary line breaking into two pieces that is itself symmetric around the origin will result in probability half on each side of the boundary. So you would also work if I did y equals x as the boundary between the two regions, or y equals x cubed, or any other curve on the xy plane that's symmetric around the origin. So that's pretty neat. And I think that the book is kind of like they were hoping that you would kind of think about that, somewhere along the way, possibly at the end of solving the problem. If you thought about it at the beginning, that'd be fantastic. But now maybe you're more likely to think about that at the beginning of a problem here on out. Look for symmetries that make some of your calculus calculations easier. Okay, that's all I've got to say by way of homework recap. I'll see you later.